As we mentioned when we started talking about GDT, bonus tolerance is one of the big advantages of this method, and it's a big reason why parts that are toleranced with GDT wind up being lower cost. Now, to be honest, you do not need to understand bonus tolerance in order to do the assignments. So if you're feeling overwhelmed and this is just too much, I understand if you skip it. However, if you want to understand GDT, you might want to have a listen. So, bonus tolerance. And here's the idea. When you make a part at any size that departs from maximum material condition, you can add more tolerance. Let me see. So here's a washer. This is a metric part. Here's a washer, and it has a thickness tolerance, and it has a straightness GDT tolerance. Notice that you have a range of 0.5 of a millimeter in thickness. Could be smaller or thicker. And then you also have a straightness tolerance of 0.2. 0.5 plus 0.2, when you or your inspector makes the gauge tool for inspecting the straightness of this washer, they will make the gauge tool a fixed size. It'll be 2.7 opening. And if you made your washer close to the maximum thickness, it couldn't be bent very much. But if you made a washer that were a thin size all the way down to 2 millimeters, it could be bent more, out of straightness more, and still fit inside that gauge opening, or still fit inside the part that it's supposed to mate with. And the actual amount of bonus you get depends on the part you actually make. We'll look at that in just a minute. And by the way, GDT is full of acronyms, and one of them that we've seen before is AME, which is short for actual mating envelope. That is the space that the actual part fits in. Alright, so here's a drawing of a block with two holes, and it's got plus minus tolerances on it. Sorry, those numbers are small in this zoom scale. So plus minus tolerances. Here we made an actual part, and the tolerance zones are square tolerance zones because we use plus minus tolerances. At the bottom of this slide is the same part, but now we've used geometric tolerancing. We've used a position control, and we've said the tolerance zone is diameter such and such when the part is at MMC. And what you see illustrated is that when you make the actual part with the smallest holes, you're limited to the smallest size tolerance zone. But if you make a part with bigger holes, you get a bigger tolerance zone. That part will still fit over the mating part. So let's say this block with the holes is supposed to fit over this thing with the two pins. And as you might picture, if you make a part with smaller actual holes, you have to be closer to true position in order for the thing to fit over the pins. However, if you make the part with holes on the larger size, they could be way out of whack, and this part will still drop over those pins. That's the basic idea behind allowing yourself a bonus tolerance. And yes, I have totally exaggerated the sizes for the purposes of making a point. You would never actually make a part that was have that much size difference and that much tolerance difference. So when you have a part that has an M in the feature control frame, that means you can have a bonus tolerance. this part has 3 different geometric tolerances. There's a slot, a hole position, and another hole position. So here's the geometric tolerance on that slot position. Here's the geometric tolerance on the smaller hole position. And here's the geometric tolerance on the bigger hole position. And when you have a tolerance with an M in it, that means your inspector can inspect the part with a fixed size gauge. In the next presentation, the next lecture, we'll talk about how they figure out the gauge size. But for now, we'll just say the gauge can be a fixed size when you see an M in there. And let's think about the bonus tolerance. So here is a block with a pin on it, and it has a size range from 12.2 to 12.6 millimeters. And here is a perpendicularity tolerance, and this says the pin, the center axis of the pin must be perpendicular within a tolerance zone that's 0.3 in diameter when that pin is made at maximum material condition. And what is the MMC of that pin? It's 12.6. That's the biggest that pin could be. So let's fill in this bonus tolerance table. If you make an actual pin, the actual mating envelope is 12.6. The perpendicularity tolerance is 0.3. That's what it says in the box. There's no bonus in this case because you made it at maximum size, so the tolerance is 0.3. What if you make a part where the pin is a little bit smaller? It's 12.5. So you still had a perpendicularity tolerance of 0.3, but now you have departed from MMC by 0.1 of a millimeter. So you get to add a bonus of 0.1. So now you get a total tolerance of 0.4. What if you make a part that's 12.4? You get a bonus tolerance of 0.2. You've departed from MMC by 0.2. And so now you get a tolerance zone of 0.5. And 12.3, you get an even, oops, I goofed up there. You get an even bigger bonus tolerance. Don't look at that 0.2, that's wrong. And if you make a pin at 12.2, you get a bonus tolerance of 0.4, and so the biggest tolerance zone. Now here's a mating part with a block with a hole. If you make the part with the actual mating envelope, the actual hole at its MMC, the smallest hole, you don't get a bonus. But as you depart from MMC, you can add, if you've departed by 0.1, you can add a bonus of 0.1, so your total tolerance is 0.4. If you depart more, you get a bonus tolerance of more. And if you make a part with the hole at least material condition, so the biggest hole, you get to add the most bonus tolerance, and you get the biggest tolerance zone. And notice that in both these examples, if you want to think about how much bonus can you add, you look at what is the size difference between these limits dimensions. The pin has a size difference of 0.4. That's the most bonus tolerance you could get. The hole has a size difference allowable of 0.4. That's the bonus tolerance you could conceivably get. I'm going to skip this. So here's an example where you could apply it. Here's this block again. Let me show the block with all that gobbledygook whited out. So let's just think about the position of this little hole. So here's the size tolerance, 6 to 6.6. Here's the position tolerance, 0.2 when it's made at MMC. All right, we're out in the inspection lab, and we find a part where the actual part had a hole that was 6.1. So that's within the size tolerance. It has a position error. The position is out of whack by 0.4. Is that a good part? Thinking about bonus tolerance. Well, let's figure that out. So we'll make a bonus tolerance chart here. We made an actual hole of 6.1 diameter. We start with a position tolerance of 0.2. The tolerance zone is a diameter of 0.2, but because we have departed from the smallest MMC size, we've departed by 0.1, so we can add a bonus tolerance of 0.1 to our original tolerance, so we get a total tolerance of 0.3. Is this a good part? No, it's not, because we get with our bonus, we get a tolerance of 0.3, but this thing is out of whack by 0.4. So no, it won't work. But what if you come along and you drill out the hole? And you may have done this on objects in your life, I don't know. If something won't fit, you drill it out. So let's say now we drill out that hole. It's still out of whack. It's out of position, but we make it bigger. So now the actual hole is 6.2. We start with an original tolerance of 0.2, but now we get to add a bonus of 0.2 because we departed from MMC. We're now, instead of 6.0, we're at 6.2. We've departed by 0.2 in size, so that's our bonus we get to add. So now the total tolerance we're allowed is 0.4. So how much position error could we have now with our bigger hole? We could have 0.4. Is it a good part now? Yes, it is. We're now allowed a tolerance of 0.4, and we're out of whack by 0.4, so that thing will work. Here's this slide again. We saw this slide earlier. This was slide 5, but I just wanted to put it in here again, illustrating the point that we were just running through by drilling out our hole. When we have a bigger hole, we can be out of position by more and still have parts that will assemble. And when you are putting geometric tolerances on drawings, as we see here, here's an example, position control, tolerancing the locations of those four holes. When you put a thing on your GDT on your drawing, if you have an M in your position tolerance, that means a bonus tolerance is allowed. And what that means to your inspector is they can use a fixed size gauge to check this part. So here at the bottom is an imaginary gauge. These brown things are gauge pins. Your inspector makes those gauge pins a fixed size, knowing that if the hole is bigger, they get a bonus tolerance and it can slop around more. If the actual hole is smaller, they get less tolerance and it has to fit more tightly. But once they've figured out what size to make those pins, they don't have to measure everything under the sun. They just drop the part over the fixed size pins. If it goes on, it's a good part. Saves a huge amount of time.